Today is the third and final lecture of Fiala. Shanahan telling us this time about machine learning for sampling probability distributions in lattice field theory.
Okay, thank you very much. So this is the sort of technical lecture where I make good on some of my hints from the colloquium to tell you a little bit about how we can use machine learning to sample the very high dimensional probability distributions that appear in lattice field theory. Now, lattice field theory, okay, is maybe a bit of a niche topic for a general audience. So the goal is also to explain how you might really use custom physics-informed machine learning to solve a physics problem and give you an example of doing that and what I mean by custom physics-informed machine learning. So starting from physics principles, symmetries and variances, and building a machine learning framework from the ground up for that problem. That can be applied in many contexts, not just lattice field theory. But before we get going, a reminder of the motivation. So in my colloquium, I talked a little bit about how some of the advances in our understanding of the standard model and studying really from first principles, especially the strong interaction part of the standard model, is giving us new insights into the structure of the proton and neutron, the structure and interactions of nuclei. But I also showed you some problems that we'd really love to solve if only it were computationally feasible. So for example, although we now have real precision results, we're in a precision era for calculations of various aspects of the three-dimensional structure of the proton. I told you about the proton's pressure distribution and shear that we've been able to compute for the very first time just in the last year. There are questions like muon g minus 2, where there's only just beginning to be enough precision in first principles calculations to compare to the very interesting tension between the best experimental result and the consensus theory value that's data-driven, not from first principles. And also, calculations of nuclei. I showed you some very first principles calculations of nuclear structure, but wouldn't it be great if we could start from the standard model and do Big Bang nucleosynthesis, not just the first step, but go all the way to lithium and say something about the lithium abundance from first principles, right? These are the sort of dreams that if only we could break through some computational ceilings, we know how to do. Okay, so when we're in this situation, we have really extreme computational challenges. Even the calculations that we can do would take 250,000 years on this laptop. They take years of accumulating statistics on the world's largest supercomputers. You say, okay, there have been major advances in machine learning. Can we use those to solve some of these extreme computational problems? It seems like a natural fit. Of course, then you go back and say, but wait, we're talking about first principles theoretical physics calculations. I want them to be rigorous. I want them to truly be first principles. And now you want to bring machine learning into them. How does that work? And the answer is, in this case, when the problems we're trying to solve are defined by equations, they're rigorously defined, we want rigorous answers, the only thing machine learning can do for me is get me to the same answers faster, right? There is no scenario in which I'm looking for a different answer. I'm trying to do essentially an integral that has a well-defined answer. And machine learning can potentially get me that answer faster, or get me that answer when it's not computationally tractable any other way. But it has to get me that same number, no matter what I do. So this is true in, say, lattice field theory calculations, but also plenty of other first principles theoretical physics calculations where the problem is defined by a set of equations, and that has a mathematically rigorous answer. So the way to use machine learning in this context, where you have no room for approximations, no room for modeling, no room for errors, is to set up your system like this, where the algorithm is designed in such a way that if it's poorly trained, before you've even optimized your machine learning part at all, you're guaranteed to get the right answer. It might just be very slow, so slow that it's not practical. And as you train your algorithm, as you optimize, well, you're still guaranteed to get the right answer because that's built into the structure of your algorithm. Just ideally, it's now much, much faster. And that much faster might be the difference between a calculation that's possible and one that's just not feasible, even on current best hardware. So how do you set up a scenario like this? I gave you some hints during the colloquium. I'll remind us, since not everyone would have been at the colloquium, and then I'll go into a great amount of detail on one example in particular. So there's a number of ways of getting from, it's always the same starting point, the equations of your theory, to the end point, which is your provably exact theoretical physics calculation, faster with machine learning. And the first is really the least interesting, but sometimes very effective. It's do the calculation the same way, but faster, which in this cartoon means I'm running on exactly the same road. I'm just going faster along that road with the power of machine learning. And examples of this would be I have a classical algorithm with many free parameters defining that algorithm, and I can tune those parameters using machine learning. So in this case, none of the guarantees have changed because you're still using the same algorithm. So if it was exact before, it's still exact. It's just that you're using it more efficiently. So this is perhaps not very interesting. It can be very effective. Some examples, I'm going to keep using the example of solving a linear system because that happens in many contexts. The state-of-the-art algorithm for solving linear systems is algebraic multigrid. It has many free parameters. And we've shown that you can make that much more efficient by tuning them using machine learning techniques. Okay. What about more interesting applications of machine learning? Another example is where instead of going from the same start to the same finish, we're now going to shorten the road, but still run along it with the same classical algorithm. So by that I mean we're going to transform the problem into one that's easier to solve, and then you use your standard techniques with the standard guarantees of exactness to solve it, but you've transformed the problem first, right? So examples of this, again, let's think about solving linear systems. Preconditioning of any type. You're trying to invert a matrix. If you can have a matrix that's almost its inverse, you can precondition both sides of the equation, have something with a much better condition number, solve it with your standard matrix inversion algorithm, and then undo that at the end. So if you could say, have a matrix preconditioner that's machine learnable, you keep all your same guarantees of exactness, but you solve the system faster. Another example is change of variables falls into this category. And an example I particularly like is contour deformation, standard complex integral. You can deform the contour any way you like, and as long as you don't cross a pole, the answer is guaranteed to be the same. If you can parameterize that contour deformation in such a way that it can be optimized or machine learned, then you might be able to have a contour that's much more numerically tractable, but is still guaranteed to have the same answer, right? So that's a second example. A third example is to solve, well, a different problem entirely that might be much easier to solve, as long as you have a way of correcting and guaranteeing at the end that you still end up in the same place, your provably exact theoretical physics calculations, right? And so examples of this would be if you're trying to compute some observable and you can map to a different observable and then correct. An example in the context of linear systems, which I've been using, is to do sloppy solves, so not quite as high precision solves that you then know how to correct with some high precision solves. Right? An example in terms of probability distributions is if you can sample not quite the probability distribution that you want, but one nearby. As long as you have a few specific features, like you know the probability distribution that you're actually sampling, you can correct using known algorithms to get back with guarantees to the distribution you're targeting in the first place. So these are all sort of generic categories of ways you might use machine learning without compromising the rigor of a first principles calculation, lattice field theory or otherwise. So now I want to go into some details of just one example in class 3, this solve a different problem, apply a known correction, that occurs in the context of lattice field theory calculations where we start from the standard model, and in particular the strong interaction part of the standard model for lattice QCD, and discretize it onto a space-time grid in such a way that you can do essentially very high-dimensional integrals to extract your quantum field theory quantities. So what does that look like? This will be familiar to those of you who came to the other lectures, but the QCD equations which essentially look like integrals over fields in the path integral formalism. Once you've discretized your theory, they just look like very high-dimensional integrals in something like 10 to the 12 variables, right? So this is what that looks like in more detail. If we want to take the expectation value of some operator to compute some observable, this is my QCD path integral over the gauge and the fermion fields. This is that operator that I'd like to compute. This is weighted by the exponential of the action. I'm in Euclidean space, so this has no I in it. Otherwise, this should look just like a familiar quantum field theory expression. If we sample the field configurations with this weighting built in, so sample them according to a probability distribution defined by the exponential of the action, then doing the lattice field theory calculations boils down to just computing your observable on that set of samples and essentially taking means and standard deviations to define your value and the uncertainty. So no matter what you're trying to compute, the first step of one of these calculations is sampling according to this probability distribution given by the action is, of course, the function encoding the quarks and gluon dynamics of the theory. Okay, so what is this sampling problem mathematically? Summarized up here, I want to sample configurations, I'm going to call them phi, with this known probability distribution, and the action is a function that I can calculate, right? So for QCD, the gauge field configurations are really represented by matrices living on each edge or link of a hypercube. Of course, I'm only showing 3 dimensions here, it's really 4 dimensions. And each edge here has an SU3 matrix. So a 3 by 3 matrix with unit determinant, right? In sum, we have something like 10 to the 12 double precision numbers if you count up the degrees of freedom in every 3 by 3 matrix on every edge of a sort of typical size box. All right, so as I said, the weighted average over your physics observables computed on these samples is then what defines the physics of interest. But the problem is, how do I get order 10 to the 3 to the 10 to the 4 samples according to this distribution here, of these sets of matrices? So in the end, it's just a large-scale sampling problem in 10 to the 12 dimensions. That's it. It has this complicated structure, but it is just a sampling problem that you might encounter in many other contexts. Okay, so how do we conventionally sample these gauge field configurations? Well, it's a very nice algorithm known as hybrid or Hamiltonian Monte Carlo. And essentially, it's a walk guided by Hamiltonian dynamics through the configuration space. You randomly sample some momenta. You then evolve with Hamiltonian dynamics. And this very efficiently both explores level sets in your probability density space, but moves you between them in a way that's much more efficient than if you did just random Monte Carlo sampling in such a high-dimensional space, which would never work very effectively. Now, one of the big problems with this algorithm, as efficient as it is, it's still the best current algorithm in use, is that it really is sequential. You're making small changes from one sample to the next in a Markov chain type process. And what that means is that there's some correlation between the samples in your chain, right? At the start, there's some burn-in period. You take small changes till you equilibrate to the right probability distribution. And then you're sampling the right probability distribution, but each sample is correlated with the previous one. Now, this sampling approach, these updates, are really close to local. And what that means is you can think about the changes propagating out across the lattice like this. And so what that then means is, let's say you want to decorrelate them on the scale of some physics observable, like the size of the proton, right? As you make the lattice spacing smaller, the number of steps you need to decorrelate the physics on this fixed length scale grows. If you have a very coarse spacing, maybe you only need 2 steps to change physics on this scale. If you have a very fine spacing, you take many, many steps to change physics on this scale. So this is a manifestation of what's known as critical slowing down in this context, and it means that as you make the lattice spacing small, which is of course one of the limits we have to take to return to continuum physics, the computational cost diverges badly, right? A related problem is so-called topological freezing, or the freezing of sampling. And so if you imagine you have a chain walking around sampling this probability distribution, if you don't have a large enough momentum to jump over a potential barrier, you can end up sampling just one sector. And this is a particular problem for theories with topology. You can end up sampling just one topological sector of the theory and not others with this update-based approach. Okay, so both of these complications in some sense limit lattice field theory calculations. You can't go to arbitrarily fine lattice spacings. The computational cost diverges. Okay, so let's go back to this problem. This is the problem we'd like to solve and why conventional methods aren't enough. Let's visualize what it looks like. So I want to sample configurations with this set probability distribution. Again, I can calculate the action. What that really means is if these are visualizations of field theory configurations, I want to sample these, which have correlations on sort of some canonical scale that you can see by eye, much more frequently than I want to sample this. This is just random noise. This is very unlikely. This is very likely. I want to sample these more frequently than that. And there's, again, an immediate and clear parallel to a problem that's got a lot of attention in the machine learning community, which is the problem of image generation. And so the first thought is, if there are algorithms that are very, very successful at generating samples like this and not this, so good pictures of people's faces and not random noise, maybe a similar algorithm would be good at generating these good field theory configurations and not this random noise, right? It seems like a natural fit. If you look more closely into it, there are immediate and clear parallels. There's also immediate and clear differences. So the first, it's only the set or ensemble of the gauge fields that has any meaning at all. They must follow this known probability distribution. Whereas each picture of someone's face is a good picture of a face or not entirely on its own merits. It doesn't depend on the distribution, right? So a clear difference in target. Then you have a clear difference in the data hierarchy. So in this benchmark image set for machine learning, each image is defined by something like 3,000 numbers, but you might have 60,000 samples available to train your algorithm on. In comparison, each gauge field is defined by something like 10 to the 9 to 10 to the 12 numbers, and you might end up with a few thousand. Take the ratio of these numbers compared to the ratio of these numbers, you have an extreme inversion of the typical data hierarchy used in machine learning problems. And that tells you that anything that involves training data isn't going to work. Another way of thinking about that is, if I want to use machine learning to generate my samples, well, if I already had the samples, I wouldn't need to be using machine learning to get them, right? I want to use this for examples where I can't use conventional algorithms to get my samples in the first place. So no training data. Physics is really defined by long distance correlations, right? Govern a lot of the physics. In pictures of people's faces, it's local structures, an eye, a nose, a mouth, that have really motivated things like the development of convolutional neural networks. Is particularly good for problems with those types of local structures, which is the opposite in some sense of what we have in our field theory configurations. We have symmetries that just don't even make sense in the image context. So we have rotations and translations in 4 dimensions with boundary conditions. These things would look different as images, especially if you include sort of a 4-dimensional rotation and translation, but they're identical as far as gauge field configurations go and should be generated with identical probability. But even more so, remember that what we really have is a matrix on each edge of this lattice, this hypercube, and there's a gauge transformation that relates field configurations in this way. So this is our matrix on the edge here. I'm going to left and right multiply by different SU3 matrices, but in a correlated way across the whole lattice. And what that does is it takes a configuration that has identical matrices on every edge and turns it into one that has different matrices on every edge, but these are identical from the physics perspective. So these two samples are exactly the same. They're related by a fundamental symmetry. Okay, so clearly you can't take an algorithm, off the shelf used for images and apply it to these sorts of problems. You really have to start from the ground up and design a custom machine learning algorithm for these sorts of problems. And just again, advertising the Boston Area Institute IFI that involves both MIT and Harvard is really dedicated to these sorts of problems. How can you use machine learning, but applied to these sorts of physics problems where you need to redesign everything from the ground up with physics principles built in? Okay, so this sampling problem, one way of tackling it with machine learning is via what are called flow models. And the idea behind flow models is pretty straightforwardly a change of variables. We're going to machine learn a map between probability distributions. Here on the left, I have what's called the base distribution, and the idea is that this is something that's easy to sample. So have in your mind something like Gaussian, something very easy to take many samples from efficiently. And on the right, the model distribution, which is the distribution ideally that you'd really like to be sampling from, the one that's difficult to sample from via traditional means. Between them is a flow transformation, and what makes this map a flow is that it's invertible, it's one-to-one, and it has a tractable Jacobian. What makes this a machine-learned flow is that this map has many, many free parameters that you can optimize or learn or train, right? So if you have maps like this between probability distributions of interest, it's very, very useful, right? The first and most obvious is that, well, you could use it as an approximate trivializing map, meaning that this could be an efficient to sample base distribution. This could be the distribution that I want. the exponential of the action, and then, well, I have an independent sampling method. It's not serial at all. I take samples from the base distribution, I put them through my map, out come samples of the target, and I'm done. This is embarrassingly parallelizable, very efficient on computing, no updating from one step to another, no correlations at all. This would be fantastic, right? Well, there are also ways of making this exact, and there are also ways of training this if you can define such a map between distributions. So training, all you need is to be able to define a function to minimize, whose minimum is in fact that the model probability distribution is the one that you're targeting. And you can do that in a way that doesn't require training data. This function that I've written down here has its minimum where Q, that's the model distribution, is equal to the thing I'd like it to be equal to. And if you stare at this function, you can see that this can be computed stochastically just by drawing samples from the model, that is by drawing samples with probability Q. Right? I draw samples with probability Q, then I just compute this part, and that's a function that I can minimize. One way of understanding what that equation is showing you is saying, I can take a sample from the model, push it through the map, and say, with what probability was this generated? And with what probability should it have been generated, since I can calculate the action and minimize the difference between the two, right? So you don't need samples from the target distribution to start with. You just need your map, and you can optimize by self-training. What if this is not exactly the distribution you really want? Well, you can guarantee exactness either via simply reweighting, since again, you can calculate with what probability was this generated and with what probability should it have been generated. So you can reweight with that ratio. Or you could use a Metropolis-Hastings accept-reject step, so accept or reject configurations with a particular probability. So both of these approaches guarantee you exactness in the limit of a large number of samples, which is exactly the same guarantee conventional algorithms have anyway. Okay, so I'm going to go through and show you that applications of this in Lattice QCD have been very effective so far in proof of principle applications, that they overcome this critical slowing down and topological freezing, essentially because you don't have a chain anymore. So the critical slowing down increase of correlations doesn't make sense if you have no more correlations, right? You have very efficient parameter space exploration, which you can imagine if I say you go from a trivial theory to one of interest. If we're now interested in a slightly different theory, well, it's very easy to just retrain the map slightly to point to a different place, which means if you want to change the quark masses in your calculation slightly, change the strong coupling, you don't need to do all the training from scratch again. You can simply reuse. You actually get direct access to the partition function, which is conventionally very hard to compute in lattice field theory calculations. However, this is only one of many approaches to using flow models in this context. As well as direct sampling, there are various hybrid approaches. You can map from one theory to another theory, which, as I'll show you at the end, lets you really exploit correlations between sampling for different theories, which, if you're interested in derivatives with respect to certain parameters of your theory, can get you much, much, much more efficient calculations. There's no way with conventional sampling approaches of getting correlated samples for different theories, say at different quark masses or at different values of the strong coupling. And the same maps can be used in things like contour deformation approaches to sign problems. Remember I mentioned deforming the contour for a complex variable before? You can do the same sort of thing with field theory, and it's a very promising way of getting around sign problems. And you can use the same architectures, the same maps in that context too. So not just for sampling. Okay, so all of this then brings us down to what the sort of underlying problem is. What do we need to do? And we need to engineer maps between probability distributions that are diffeomorphisms, so that's isomorphisms of the smooth manifold, such that both the function and its inverse are smooth, that are flexible and expressive, can encode correlations at the physically relevant scales, encode all of the various symmetries of our physics theory. So that's what I mean by design machine learning from the ground up for the problem. In this case, it's instead of writing down a neural network, how do I write down this map with many free parameters that's sort of my physics neural network that I can then optimize for the problem, right? Okay, and once I have it, just a reminder of one of the ways you can use this very efficiently for sampling is you have your map, you optimize it, and you optimize it by drawing samples from the model, computing the loss function and doing gradient descent, iterating. You save the model, so no training data was required, it was self-training. You make a Markov chain using samples from the model or reweight them, and all of your sample generations now embarrassingly parallel, very efficient to parallelize on supercomputers. Okay, so doing this has really been an ongoing problem, an ongoing project in my group since 2019, involving a sort of rotating cast of extremely able junior researchers. This is some of the current crop. A few have now moved on to their own faculty positions at Bern and the University of Edinburgh, but are still working on this project with me. A few are current students and postdocs. Ryan is graduating this year, and he is really extraordinary. And since 2019, we've really built this up step by step, which gives me an opportunity to really walk you through this from sort of the simplest applications through to the complex applications for QCD, because the story of how this research program has evolved is also actually sort of a story of how to develop machine learning models from the ground up for this type of application and all of the steps involved. So first, how do you use these types of flow architectures for a field theory, a scalar field theory that's very similar to images? What about gauge field theories? How do you deal with compact connected manifolds, and then how do you deal with abelian and non-abelian field theories? What about fermions? How do they come into it? And then at the end, how do you apply to QCD in 4 dimensions? And how can you get physics observables out of this sort of an approach? Okay, so application to scalar field theory. So this is very, very similar to the image generation problem. And so this is naturally also where we started. Because in a scalar field theory, the field configurations in 2 dimensions look exactly like images. They look like this. So in this case, the action of the theory has some kinetic terms, we have a mass term, and a quartic coupling here. So the free parameters here are m and lambda. In QCD, the free parameters would be like the quark masses and the strong coupling. In the scalar field theory, here are fields phi defined on lattice sites x. That's what we're showing here. These are the fields phi, and these are the free parameters. And so I want to sample the field configurations phi with the probability distribution given by the exponential of this function here. So as you can see, you can just write down the action. There's something you can compute, right? Given a phi, a lambda, and an m, you can calculate this function here. And this is the probability distribution defined. So since they look a lot like images, you can use algorithms that were originally developed for images or variations thereof. You can tweak them to this sort of an application. And one way of doing that is to use what are called real non-volume preserving flows. And let me step through it. You can build this function out of a series of different what are called coupling layers. Each layer looks something like this. You split the variables. You could choose a checkerboard, or you could choose some sort of physically motivated variable splitting. It doesn't matter. As long as you split the variables, you're going to leave one half the same. So the green ones here, they're just staying the same. That's what this means. We're not going to change them inside this coupling layer here. The black variables, I'm going to add to them a translation and multiply them by a scaling to get the updated variables in this layer. So that's what I'm showing here. The green ones just stay the same. The black ones, Z gets updated by adding a translation and multiplying by a scaling factor. Now, this function here, t, that's a function only of the ZA, the green variables, the ones that are not changed in this layer. Similarly, the S is a function only of the ZA, only of the variables that are not updated in this layer. What that means is that these 2 functions, S and T, they can be absolutely arbitrary. They can in fact be defined by neural networks if you like. And no matter what they are, you have a transformation that has an upper or lower triangular Jacobian and is very easy to invert. If you compose this, you still have a Jacobian that's very easy to compute because of the upper or lower triangular nature of it. And so you still have invertibility, it's one-to-one, despite having arbitrary neural networks sitting inside your transformation layers here, right? So you should visualize what's happening here is you choose some prior distribution. Here you could choose it to be Gaussian. The scalar fields are just a real number at every site of the lattice. Just looks like these pixels here. Gaussian distributions. Then you define some number of these coupling layers. So you could use these real non-volume preserving coupling layers that I talked about. You need to choose some variable splitting. Here, say, choose an alternating check border pattern. And then you need to define inside each layer where all the free parameters are. So they could be hitting in neural networks with some number of layers and hidden units are sitting inside the S and the T here of each of these layers. Then you optimize it. You can train this shifted KL, Kullback-Leibler divergence. That's just the name for the loss I showed you on the other slide, something that you can write down whose minimum is where you'd like it to be. And then at some point you stop and you draw samples from your model. Right? So that's the overall picture. And we did this, and in fact it works. So what I'm showing here is a demonstration of accelerated sampling at the cost of the model engineering and training in this system here. So this is on each of these three plots. On the vertical axis is cost. On the horizontal axis, on each one, moving from left to right, is moving to larger and larger system sizes. This is hybrid Monte Carlo sampling, so the conventional sampling approach. And as you can see, as you move from left to right, things become exponentially more expensive. This is another approach that you can use for sampling this theory. It's called local metropolis. The different lines on each figure are just different observables that you might be interested in. Again, moving from left to right, the cost increases exponentially. Machine learned models, it's flat left to right. These are models trained to 50% acceptance. These are models trained to 70% acceptance. Of course, if you train to higher acceptance, the cost is lower. If you train to lower acceptance, the cost is higher. It's a trade-off between the amount invested in training and the amount you spend on sampling. The fact that these are flat should be entirely unsurprising because you now have a parallel sampler. It's not serial. So there's no sense in which correlations are increasing left to right. If they're all at 50% acceptance, the cost will be the same no matter how large. Okay. So this was sort of the first demonstration that you can get around this type of critical slowing down with this approach. This is now out of date by orders of magnitude because development of the architecture really matters. So you can make these approaches much, much more efficient by not just adapting something originally used for images, but designing something with the physics built in, how you do the variable splitting to account for physics correlations and so on. But more interesting, I want to talk about, well, what about more interesting physics theories that have gauge symmetries, where you don't just have a real number, where the variables don't look anything like images? How do we do that? And so this really comes in two pieces. The very first problem that you have to solve is, well, gauge fields, they live on compact connected manifolds, not the real line. So most machine learning approaches are designed for variables that are real numbers, that live on the real line. What if you have variables that live on a circle? How do you deal with that such that you can apply machine learning techniques? Secondly, what about all of the symmetries of the probability distribution? Now, it's true that encoding the symmetries is actually not essential for correctness. If you're using an approach where you're sampling a different distribution and you can correct, well, you're going to have to be able to correct for every way in which it's inexact, including if the symmetries aren't respected. However, if you have a 10 to the 12 dimensional distribution with a 10 to the 12 dimensional symmetry group, it's completely impractical to try to correct for that symmetry not being respected exactly. So you can visualize that here. If you have some degrees of freedom, in fact, many degrees of freedom in which your probability distribution is entirely flat, it's obviously much more efficient to write down a function that's flat in those dimensions and optimize it than to try to optimize or learn those flat directions. Okay, so it's really crucial in practice. So, well, what about flows on circular degrees of freedom? So this is really an example of, you just go back to the definition. What do you want to write down? You want to write down a diffeomorphism on degrees of freedom on a circle. So an isomorphism of these manifolds, so that the function is inverse is smooth. And you can write down the conditions required for it to be a diffeomorphism, right? If you write down a function that obeys these various conditions with some free parameters, well, you can make it more complicated and more expressive by combining functions like this under composition or combining them under convex combinations, right? So everything boils down to, how can I write down a function with free parameters that satisfies the properties of it being a diffeomorphism and is also something that's tractable to compute? Well, there's a number of ways you could do that, right? So this is what's called a Mobius transformation on the circle. It's taking this number z and mapping it to h omega z. So this transformation is parameterized by omega. But what you do is draw this chord through the circle back across the diameter, right? So this basically expands the part of the circle near omega and contracts the rest. That's what this is doing here. So this does not become more expressive under composition, but you can take combinations thereof. It becomes not analytically invertible, but it can be numerically invertible using a bisection search, right? So these are the types of considerations, but you can write down this sort of negative transformation on a circle. You can write down circular splines, right? And these become more and more expressive the higher order you go to here, the increasing numbers of segments that you go to. There are several conditions on the coefficients to guarantee a diffeomorphism, so then your optimization problem is a little bit constrained because you have to make sure those coefficients continue to obey the appropriate conditions. You can write down non-compact projections, essentially project to the real line and back again. Again, you have to be careful. This is not actually defined at the endpoints, but the gradient is, so you can extend by continuity. But then actually computing near the endpoints is unstable, so you really have to define it through a Taylor expansion around the endpoints to get away with things numerically. But again, you can define native transformations on the circle, which have some free parameters that you could optimize. Okay, so we don't have variables on the circle, we have gauge field configurations. What does that look like? Well, each of these coupling layers has to map you from whatever your group element is. And you could think about, if you like, first doing a U1 field theory, where on every edge you do just have a variable on the circle, so a U1 variable. So your group elements, and you have the number of space-time dimensions times the lattice volume, number of these group elements, one on every edge, right? And the coupling layer has to map you from that dimensionality back to that dimensionality. And one of the key pieces that made this feasible and have a tractable Jacobian was to split the variables. So whatever you write down, you have to split the variables into some that are updated by the layer and some that are frozen by the layer. Okay, there's a number of ways you can do this. I'm going to talk a little bit through two. One is what are called residual flows, where you transform the links through what you could think of as parameterized smearing steps, bringing in information from nearby links, or through what are called spectral flows, which, as you'll see, is really thinking about the spectrum of those SUN or UN matrices, the eigenvalue spectra. So residual flows are really basically a field theory version of what you might have heard of as ResNets in the machine learning literature. ResNets are really machine learning models by which you transform variables by adding a parameterized shift. Okay? So this is a similar thing. We're not going to add a parameterized shift, but we're going to transform the variables. So these are the variables that are updated. These are their original values. And I'm going to multiply by this parameterized element-wise multiplication. And sitting up here is a Lie algebra valued derivative. And this is some sort of a gauge-invariant function. Doesn't matter what it is, as long as it's a function only of the untransformed variables. So remember, in the easy case, the scalar field theory case, I had those scalings and translations that were functions only of the untransformed variables. It's the same thing here, except they're sitting inside here in this this piece. So this epsilon here, there's a Lipschitz continuity condition that will guarantee that the inverse is unique as long as this epsilon is small enough. It's something like 1/8. And so you can derive that and show that this is a, say, gauge invariant or gauge equivariant type of transformation on the gauge fields. This function here, it can be anything you like, but one example would be to define it in terms of traced plaquettes. So take all the links around some elementary loop, say a square, take the trace that's here, have some arbitrary coefficients. These coefficients could be machine learned. Those are some of the free parameters in your theory, just like the parameters of neural networks were in the previous example. That goes up here into this function. So this is one way of writing down a coupling layer with free parameters. They're sitting here. That's gauge equivariant. Another way that maybe feels a little more natural is what are called spectral flows. And so here the idea is it's really hard to write down something that's equivariant under a gauge transformation, because a gauge transformation is this complicated thing where you do something different at the left and the right of your object, right? It's much easier to write down functions that transform under a symmetry where you left and right multiply by the same thing. So what if I first reduce my problem to transforming variables that have a simpler gauge transformation and project that difference out? So that's the idea here, that this is the link updated by the coupling layer. But first, I'm going to take my variables and compose them into a loop that starts and ends at the same point. I'll transform that conditioned on the other half of the variables, and then uncompose it to get pushed back the change onto the single link. I'm going to show this in a diagram. So this then means that the coupling layer is equivariant under the much, much simpler condition that it only needs to be equivariant under left and right multiplication by the same matrix at every point. So what are we really doing there? I want to change the matrix that lives on this edge here, on this link. I'm going to take a product of these such that we have a loop that starts and ends at the same point. I'm not tracing this. This is not a plaquette. It's just a matrix-valued object that has a simpler gauge transformation property. If we have a U1 field theory and each of these is just a variable on a circle, so is this product object. I'll transform that using any of the transformations for circular variables that I talked about before, right? So I can condition that transformation on, say, these plaquettes sitting here, anything that's frozen in the layer. And then I can push back the transformation onto the link variable itself. It's sort of passively updating this plaquette here, but I transform this and push the transformation back onto the link. That's just transforming this one link here. Of course, you could transform stripes of links in the blue in every layer. The next layer, you'll transform different stripes of links and so on until you've transformed everything across the whole lattice in your ultimate function. Okay, so what does this really look like? For a non-abelian field theory, you have to write down transformations that, it's non-trivial to write down a function that is equivariant under this left and right multiplication by the same variable. But in fact, if you go down into the group theory, you see that each conjugacy class in SUN or UN is really the set of all matrices with the same eigenvalue spectrum. And so what these updates should do is move weight between different n-tuples of eigenvalues while leaving the eigenvector structures the same. So as soon as you know that that's really what you're trying to do, you're trying to shift weight between different sets of eigenvalues and leave the eigenvectors the same, then you can write down a function that does that, in fact. And so that's what this onion plot here is showing. I want to update this. Okay, let me first form the product of links around a square so it has an easier transformation property. Let's do an eigendecomposition and extract the angular coordinates, right? Now let's transform those. So that's doing a flow on those angular coordinates in that canonical cell. Then you invert them, you recover the eigenvalues, you do an eigenrecomposition, and you push the transformation back onto your link variable. So that's what's shown here. So for a SU2, SU3, SU4 type variables, in SU2 you have two angular coordinates. You extract them, then you canonicalize the ordering. So you take just one ordering, one canonical cell. For SU3, there's 6 cells. You push everything into one, you transform there, and you push it all back again. And so what you really want to imagine is happening is you're writing down a function that on every link across the lattice, there's all of these complicated pieces involved. You're eigendecomposing, eigenrecomposing, but in the middle, there's functions with a lot of free parameters that you can optimize, right? That you can then train. So this figure should look pretty familiar. It looked exactly the same when I was talking about scalar field theories that look a lot like images. Just now, we have a gauge field theory. So here's an action for a U1 field theory. This is just real plaquettes, so traced links around a loop here. This is the parameter of the theory, the coupling. This is the e to the minus this is the probability distribution we're trying to sample. You choose some prior distribution. Each of these is just a variable on the circle, on each edge, right? You can just choose uniform distributions on the circle. You write down a number of coupling layers. So you could write down 24 coupling layers, and what's doing the transformation in the middle? Well, you can choose any of the transformations on the circle that I said that are acting inside this eigendecomposition recomposition step. For example, non-compact projections. And the variables of those non-compact projections, well, those could be the output of neural networks, where the input to those of all of the untransformed variables. So the output of the neural networks gives you the parameters of the non-compact projections. Then you optimize it, and then you sample, right? So this feels like an extraordinarily complicated function that we've written down, but we just started from the ground up. We said, what do we really want? Well, we want to move weight between n tuples of eigenvalues while keeping eigenvectors. How do I write down a function that does that with as many free parameters as possible? And then you go and optimize that. And this, in fact, works very efficiently for U1 field theories. So that's just what I'm showing here. So this is a field theory where conventional sampling approaches tend to get stuck in topological sectors. So this is the topological charge, which you like is the winding number of the gauge field. Singer index theorem tells you that it's quantized. That's why this looks quantized here. So this is the topological charge. This is the step in the Markov chain. The blue here is the conventional sampling approach. And you can see you're going many steps in the chain, and this topological charge quantity is just staying the same, basically. It's because it's stuck in one of those topological sectors. It's just walking around and not changing the topology. This is another conventional sampling approach called heat bath. It's changing the topology a little bit more, but still not very efficiently. The machine learning approach, as you can see, is the orange in the background, is just swapping between topological sectors all the time. And again, that should be obvious because it's not a chain, right? So each sample has nothing to do with the previous one, so it can't be stuck in a sector. So what this translates to is a significant cost reduction. This is the integrated autocorrelation time, so that's basically how correlated the samples are in the chain. And in fact, this is a very good measure of cost here. This is the coupling of the theory. You see it here. As you go to larger couplings here, the conventional sampling approaches get exponentially more expensive. This is the critical slowing down issue. This is the flow-based sampling. It remains almost horizontal. Now, the almost is important. Why does it go up a little bit at the end? It's because training gets harder as you move to larger coupling. Right? So there's a trade-off between how much resources do you invest in training and optimizing the algorithm versus the payback in how efficient the sampling is at the end. Over here, though, you have orders of magnitude more efficient sampling, and the cost here of the HMC per sample is about the same as the flow. So this is a genuine comparison you can make.
Change the orange line.
Yeah, so each of these is a separate training. So you fix the coupling, then you optimize your sampling, your flow. You can retrain, so you can take the one trained for 4 and then re-optimize for 5, but it's still a separate model for each parameter.
Does it, the amount of training changes the curve?
Yes, so if you didn't train at all, this orange line would be way up here. Yeah, so as you optimize, it comes down. Yeah. Okay, so this A shows that this can work for gauge fields. It also shows the trade-off between the time you spend bringing the line down and then the benefits that you reap by having a much more efficient sampler. Okay, theories with fermions. Okay, so in principle, fermions are just fine. So what they do is they change the action. So here's the action that we had before, but now I'm adding fermions. So when you do lattice field theory calculations with fermions, you can actually integrate out the fermions explicitly, analytically. And all that's left is this fermion determinant in the action. And so life's good. If you can compute this, you can use exactly the same architectures that I talked about before, and everything works beautifully. So here's an example application to a Schwinger model, so 1+1 dimensional QED, if you like, with 2 fermion flavors, using exactly the same models that I showed you before. This is an observable. It happens to be the chiral condensate. And what you see is that the parameters have been tuned here such that conventional algorithms fail. These are conventional sampling algorithms. The errors go down with square root of n. It's converging to the wrong thing. That's because it's stuck in a topological sector. It's not really sampling efficiently. If you start many HMC streams, so many streams of conventional sampling, you start them and they start in different sectors and you get some sort of averaging, right? But it really doesn't work efficiently. The flow-based sampling converges to the correct value very efficiently, again, because it's not a sequential approach. You should be expecting that. However, that's really expensive to compute. In real scale calculations, you can't compute it. So you need to do something else. You can't just use the same approaches because this action, remember, being able to compute that action was sort of a key part of this. You say, I can compute the probability. So with what probability was it generated and with what probability should it have been generated? I'm going to minimize the difference. If you can't calculate the probability with which it should have been generated, you're sort of hosed from the start. So you need to use a more scalable approach, which means you need to not calculate this fermion determinant piece. So what you can show is that you can rewrite determinant of the d dagger as this integral by introducing new auxiliary degrees of freedom. They're called pseudo-fermion fields. And then this integral, it seems sort of horrible, right? I start with a nice, neat determinant. Suddenly I'm introducing new variables and I have to integrate over them. But you can do this integral stochastically. And so this is a much more scalable way of trying to treat this term. But then I've introduced new fields. And remember, my flow is a one-to-one map between all of the fields in the problem. And so if I have new fields, I need new flow pieces. So then you need to write down joint architectures for the gauge fields, the U's, and these new auxiliary variables that you've introduced. There are many, many ways you could do that. We've written a number of papers on it. I'm just sort of going to give you a hint of one of them, which is to separate out into a marginal part, so the distribution over the U fields, and a conditional part, so the pseudo-fermion fields conditioned on those gauge fields. For the marginal part, well, you can use exactly the same architectures that I talked about before, which were maps on the U degrees of freedom. You take some random variables, you put them into a parameterized map, outcome your sample is U. But now you need to write down a conditional architecture that takes in the U's, takes in some random variable Z, and gives you out the phi's. And this needs to follow the conditional probability distribution here. So how do you do this? Well, you have to, again, respect the symmetries of the theory, but now the symmetries are involving both these pseudo-fermion fields and the gauge fields. But you can say, well, what do I really want this map to do? Again, you just go back to the mathematical definition of the problem and all the physics constraints that go into it. What I really want this map to do is to map from an uncorrelated Gaussian to a correlated Gaussian. That seems like a sort of almost trivial thing for this map to do, but that's the efficient way of estimating these determinants. So you say, I'm going to sample random variables that look like an uncorrelated Gaussian, and I want to write down a map that maps them to some correlated Gaussian that approximates this d dagger inverse that appears in my probability distribution. And I want to write that down in such a way that it respects all of the symmetries of the problem. So again, we're going to partition our variables into some that are active and some that are frozen. For the frozen variables, I know the symmetries of the problem, and I know, in fact, that if I transport this pseudo-fermion field to a neighboring site, that those are related via a parallel transport, and the parallel transport is given, in fact, by the gauge link, right? So I can combine these variables by parallel transporting. This one moves over here, but with a U built in. I can take a linear combination, and that linear combination can have some arbitrary coefficients. And you could call this a parallel transport convolutional neural network, because it looks a lot like a standard convolutional neural network taking in information from nearby sites. But you have to combine that in a gauge-equivariant way, so you have to put in the gauge fields to do the parallel transport. So you have a parallel transport convolutional network, and you can update your variables with some, the original variables with some trainable coefficients, plus your parallel transport convolutional neural network to get the update in each layer. Okay, of course, there are many other things you can do to make these types of approaches more efficient. So this is really thrown in here just for field theory students who might be wondering, I didn't say anything about some of these usual tricks. You can, of course, draw more pseudo-fermion samples at fixed gauge fields. You don't have to just draw one sample at each time. You can sample the pseudo-fermion fields much more to estimate that determinant stochastically better. What that means is this is the effective sample size, so the quality of the model. The same model can be driven to much higher quality if you just increase the number of pseudo-fermions you draw, because you're getting a better stochastic estimate of the determinant. You can use standard approaches to reduce problem difficulty using things like preconditioners. So you could either machine learn those preconditioners, or you can use standard things like what's called Hasen-Busch factorization, where you're essentially reducing the condition number of your problem. Again, you can combine all of this, and it's not one or the other, not conventional methods or the machine learn part. You can combine everything. Okay, so gauge fields, fermion fields, and in fact scalable fermion fields through pseudo-fermions, you can use them to do QCD in principle. So where are we? In 2022, we did the very first application to QCD. It was at trivial parameters, but we demonstrated that at ridiculously high statistics, so these were parameters where we could go to 65,000 samples, you might have more like 1,000 in a normal conventional calculation. And this was really to demonstrate that we have mathematical guarantees of exactness, but in fact they also hold up in practice. You have beautiful agreement between conventional sampling algorithms and the machine learned sampling for QCD. This is the topological charge. You get all of the sectors with the appropriate distribution between them. Okay, but this was trivial parameters of QCD. What about scaling up? And I'll tell you that's very much in progress, but just this year we were able to do the first exploitation of this type of approach for physics observables. And if you remember back to my colloquium, I talked about how we're just beginning to be able to measure some aspects of the gluon structure of the proton for the first time, and there's some first experimental measurements in the last 18 months or so. Well, here I'm showing an exploitation of these sorts of approaches for computing a physics observable. This is the momentum fraction of the pion carried by gluons. And what I'm comparing here is a conventional approach that's using independent ensembles. You can get at this via a derivative term. It's via a Feynman-Hellman type method for again, field theory students. Using independent ensembles, so a conventional approach. This is with float ensembles at the same statistics. So what this is really demonstrating is in a QCD calculation, it's not just about faster sampling. We'd love to get to faster sampling. At scale, we haven't demonstrated that yet. But it sort of doesn't matter, because even if you have just equivalently fast sampling, you can use these flow models in qualitatively new ways to get physics observables to do. This is exploiting correlation to different sets of parameters that you normally can't get correlated because of the sampling approaches that are used. So if you generate them in a correlated way, you can exploit that correlation to get physics observables with orders of magnitude smaller error bars at the same statistics. So this is sort of the first demonstration. And now the question is, can we really scale up and exploit this at a much larger scale for problems like G-2, dark matter direct detection, nuclear physics? And that's what we're working on right now. We have early science time on Aurora. That's the new largest supercomputer to be built in the United States. And we got access. It's still in the commissioning phase, so it's an unstable machine, but we have early access right now over the last month to try to implement our architectures and see if we can run them at scale. And so it's very exciting, very promising. Whether or not it will work right now, I don't know. It's a difficult thing because you need to scale a custom machine learning architecture to the same scale as the largest machine learning models used in industry. Think about things like ChatGPT, AlphaGo, but now we're doing this with a custom physics architecture. So that's not an easy task on the engineering side. Okay, so just the summary. This has been a sort of a several-year road, but we've gone from nothing to provably exact machine learning accelerated sampling that's orders of magnitude more efficient than conventional algorithms and overcomes important difficulties like critical slowing down, has unbiased results where conventional algorithms fail, gives qualitatively new calculational approaches, and we're trying to deploy, it's called Aurora 2023, even though we're getting access in 2024 and 25, but that's the name of the program. We're trying to deploy at scale now. And these are really all of the motivations. Can we overcome systematic limitations in a lot of the physics that I talked about in the colloquium? Things like muon G-2, proton structure, nuclear physics. Because this is targeting the first step of any lattice field theory calculation, if it works, it'll impact all of them. And okay, what are the takeaways? So the takeaways are really, you can use machine learning to compute exact results for first principles theoretical physics. You don't necessarily have to be introducing some black box, some bias, some uncertainty. It just requires designing the algorithm somewhat carefully so that you maintain your guarantees of exactness. No data set, only equations to solve, which means that machine learning can only make it faster or potentially computationally tractable, right? So there are potentially high impact applications and development across a number of contexts. I gave you one example of one application in field theory, so we could go into some detail. But as far as I can tell, what they all have in common is that you've really got to go back to the drawing board. You've got to develop the machine learning from the ground up by saying mathematically, what do I want to do and how do I then do it? Parameterize it in such a way that you can apply machine learning approaches. But secondly, they really require engineering and scaling up to the state-of-the-art machines, which, those frameworks are really new. The support for scaling custom physics-informed machine learning architecture up at scale it isn't quite there yet. So this is something that's really going to change over the next 5 years or so. We haven't seen this or other application in this area hit the big time yet, mostly because of the engineering challenges, right? You can't just use standard PyTorch. You need to build it from the ground up. And so I'm very excited of what's going to happen over the next 5 years in this area. Thank you.
So in your example for the error from the flows, is there any source of say initialization error in the training? Because there's no training data per se, right? So during training, is there zero initialization error?
Yeah, so what you want to think is that the map is, you have to write down a map that's one-to-one. So even before you've trained anything, you're guaranteed to sample everywhere in the distribution. As long as your prior has density everywhere, your sampler has density everywhere. The problem is if you write down a prior that's sort of peaky, that in principle guarantee that you will sample everywhere, might not be very much in practice, right? This is a place where actually the fact that we have compact connected manifolds sort of saves you. If you imagine you have a real line and you say, okay, I write down a Gaussian, in principle that has density everywhere, but out on the tails, does it really in practice? Am I going to see that ever? If you have a circle and you say, let's start with uniform, well, yeah, in practice, that has density everywhere right from the start, right? So there's sort of no initialization error, you just have an initialization inefficiency, where if you're reweighting, or your reweighting factors might be really low, so you need very, very many samples to get a precise result, or you'll need accept reject will always reject, so you need very, very many samples. So before training, you're still guaranteed exactness, you just won't actually be able to compute anything. The uncertainty will be so large because all of your samples will be bad. But as you take more samples, you'll converge to the right answer.
I see, thanks.
Over there's a question.
Hi, does the flow algorithm help if you want to sample over a dataset with unknown distribution?
So it depends. The way I've discussed using the flow here, the training is really relying on the fact that you know the distribution and you're using that to define the training. If you have an unknown distribution, then you need to define it in some other way, for example, through a set of samples. So you can do that if you have a set of samples that's implicitly defining your distribution, then you can do a supervised training approach where you train with that training data set. But if you have neither equation nor a set of samples defining your distribution, then sort of what are you trying to optimize? Then you're stuck. But if you can define it either explicitly with an equation or implicitly through existing samples, then you can. You just have to change the loss function that you're using for training.
Okay, thanks.
Any other questions? I have a question. So you were saying that at the end you're better off designing your own system for your own problem. I mean, but there are all these amazing technologies now available. None of them are useful in any form. Like, I don't know, let's say this stupid thing like ChatGPT. Would that be in any way useful in any part of what you're doing?
So the place they can be useful is right at the innermost level. So when I was talking about you do an eigendecomposition and a recomposition, and then in the middle, the parameters of, say, my non-compact projection or my spline, those can be the outputs of some arbitrary neural network, which could be transformer architectures or any of these modern fantastic architectures. It just has to be in the algorithm in the right place.
So you can, in principle, mix it with yours?
You very much can.
I see, but you haven't done that yet.
We have.
Oh, you have?
We're using them at the innermost levels.
I see.
But the sort of hard part is, so an example I like to give is, let's say you want to invert a matrix. The sort of naive way of using machine learning is say I'm going to take a lot of matrices and their inverses and train the latest transformer architecture to give me the inverse. You can do that. It sort of works. you never know how good the inverse you get is. It might be, if you go far outside of your sample set, it can be completely wrong, right? Or you can say, well, I'm going to take all of those samples and I'm going to train a transformer to give me a preconditioner, right? And then if you're taking matrices that are close to your samples, you precondition, your conventional inversion algorithm works very quickly. If you're far out of set, you'll get a bad preconditioner and your conventional algorithm will take a long time to converge, but you'll still get the right answer. So you're exploiting it, but you're building it in a way that you preserve the rigor of your calculation. And that building in for the matrix inverse is very easy. You just use a preconditioner. For this sort of an approach, there's a lot of layers. But.
Nice. Thank you. Any other questions? Okay, if not, let's thank Fiala for beautiful thoughts. Thank you.
Thank you.